Hello everyone, my name is Untitled Chapter, and on my project I'm going to be going over the impact and deformation analysis of a car's front impact bar. So modern automobiles are often compared to older vehicles from the 50s, the 60s, and the 70s, usually by older people that lived in that age. And one of the main points of comparisons are the big, heavy, and strong metal bumpers those old cars used to have. Modern bumpers are made out of layers of different structures and materials. Then those layers help to absorb and then dissipate the force of an impact. The innermost layer of protection can be seen as a reminiscent of those old metal bumpers. However, it is designed to assist with the energy dissipation of the impact. Here we can see what those bars look like in the real images of cars. On the left, you can see one after what was probably a collision with a light post. I would assume when you consider the shape of the deformation, and on the right side, you can see one being still mounted on a car in a perfect condition, as well as one that is not in a car, just sitting on a table where you can actually see clearly its normal shape. Car manufacturers clearly have performed tests and analysis on the materials and the design of these impact bars. However, no information was really available online, either from the manufacturers or from research papers of any kind. Therefore, this project can be a good avenue for me and for hopefully you guys to better understand the importance of this component, since not much information is available. Main objective of this project is to understand and analyze how those car front impact bar deforms in a way to absorb the energy of a frontal collision, which better protects the passengers of the vehicle, and also to visualize the different behaviors of the different materials that are commonly used in this application. Here you can see the geometries that are designed for this project. They are based on the impact bar from, I believe, 16 to 18 model year Chevy Impala. They're pretty close to the actual design of those impact bars. However, due to the fact that I didn't have real dimensions, I kind of had to design them in a closest as I could to what the real version might look like, maybe. Here you can see some of the boundary conditions of the analysis. You can see the mesh that I use. As you can see, the model that I use for the actual simulation is simplified, mainly because when I try to run a simulation with the previous model, it wouldn't work. There was something in the design that the mesh would not form; it would just fail all the time. So I use a mesh sizing on this simplified version of 20 millimeters. Here you can see that I applied a fixed support on the area of those two supports of the bar, which is actually the areas that are attached to the car, to the vehicle. And the force was, as you can see, was applied on the front part of the bar. The force applied at first was of 100,000 newtons. Here you can see the analysis performed on this using structural steel, again with a load of 100,000 newtons. There was approximately a very small deflection, way smaller than I was expecting, which is one of the reasons why I want to research a little bit more and maybe ask some people to see if the information that I put and how the model is right, because a 0.36 millimeters of deflection is very small for such a large load. However, as you can see on the deformation with a 2x deformation enhancement and a 5x, that's usually what you would expect from a hard frontal collision in one of those, in a metal bar. Here you can see the stress plots. I had a maximum value with a load of 93.485 megapascals, which is significantly smaller than the yield strength, which is, I believe, is 250 megapascals for structural steel. One thing I found interesting was the fact that the maximum load was not at the front of the bar. The maximum stress was not at the front of the bar where the load was applied, but actually at the spot where the support would attach to the bar. As you can see on the it's almost a right angle. So it was interesting to see that that was a spot that suffered the most largest amount of stress. Now we're moving to the aluminum alloy analysis, again using the same 100,000 Newton load. The aluminum had about 3 times larger deflection of 1.04 millimeters, which is again very small for such a large load. And also it was interesting to see that is the maximum stress was a bit smaller at 92.4 megapascals compared to, I believe, 93 megapascals. So it was interesting to see how the deflection was smaller, but the maximum stress was smaller. Deflection was larger, but the maximum stress was smaller. To actually see how the deformation would be at a very large load, since I wasn't getting a lot of deformation with the load that I originally put, I tried to do an analysis on the aluminum with a load of 900,000 newtons. I think, if I'm correct, the simulation wouldn't go beyond that point. You would just tell me that the deformation was too large and it wouldn't run. So at that load, I got a deflection of 13.1 millimeters, which is way bigger than the original analysis. And as you can see on the stress plot and with the maximum stress value, the metal just failed with such a large load and a maximum stress of 317 megapascals. Most of those impact bars are made of either steel or aluminum. Those are the metals that I use in the simulation. Even though I haven't really had a chance to find the very specific metals that I used, I know that they are aluminum and steel. So for now, I'm using structural steel and then a basic aluminum alloy that ANSYS Workbench provides, and both my materials were being non-linear in their settings. Here you can see some of the specifications of those materials. As you can see, structural steel has a much higher density than aluminum alloy, which is responsible for the metal being way heavier. You can imagine that a bar, there will be a significant difference in weight for a bar made of structural steel or aluminum. However, as you can see, there are slight differences in the tensile yield strength as well as the tensile ultimate strength. As you can see, also the Young modulus of the aluminum is significantly different as well. So for my next steps for this project before the final report is to again recheck my ANSYS Workbench simulations to make sure that those deformations and the values that I got are real and there's nothing wrong with them, since they were way more than I was expecting. I want to perform a simulation with stainless steel because based on what I saw in some pictures and in some websites that are not really more like resale websites for those impact bars, stainless steel is likely to be a material that those bars are also made of. I also want to research the cost versus performance of those materials and see if the higher price of using aluminum makes it up for being lighter than steel, for example, and using that information come up with a final conclusion for the project. Thank you very much.